So welcome to this session. This session is on cloud native. What we are going to do in this session is we're going to go through a 2-day session. Each of these will be a 2-hour session. It's a hands-on session. So I'm going to have theory to start with. So you are up to the speed with the labs, and then we will do the labs. We are going to set up a full stack application in a cloud. So you're going to start with a very basic application, then start wrapping it into containers, and then we'll put it into a Kubernetes cluster. So all these technologies you will learn on the way. So cloud native demo, and there is a tutorial attached with it. We'll go through these commands, so you don't need to take notes of the commands. When you run this application, so it's a client-server application. Let's say an application where a client speaks to a server, similar to when you, for example, use Google Map. You open the application, you give a source and destination address, and the map gives you the route. So I've set up a very simple application like this. We can set up, let's say, where my application or the server is running. So in my case, it's this IP address. It could be different when you do it at your machine. It could be localhost, but I'm hosting it in a different server. That's why I'm putting a different IP. And a port number here, which is 9000, and you will see where the configuration is. And what this application does is, if I say I will create a random graph of, say, 6 nodes, and I'm going to put a node prefix, say node. So the node names would be node 1, node 2, node 3 up to node 6. And I can choose between Dijkstra's shortest path algorithm or Bellman-Ford algorithm. Okay, these are the pathfinding algorithm you already know. And when you click here, it will show you a topology. And when you go down, you will see that it shows the actual adjacency list representation of the graph and the shortest paths. So between any two nodes, there's a node 1 and node 5, the shortest path is through 6. Okay. This one, for example, has no, they're like adjacent vertices, so there's just one path. So this is an application that we will onboard in a cloud. Okay. Normally, so in this session, for example, you have already done some sessions on backend and GitHub. So you already know, for example, some basics about client-server computing and version control. But the main purpose of this session is, okay, so you have the application. Now, how would you make it cloud native? Means, how would you port that application in a cloud? So that's the main objective for this session. The main idea is we're going to start with some theory. So the whole session is about cloud computing and 5G. The 5G bit you might downplay because this will be an application of cloud native. That okay, so after building a cloud, what are the different things you can do with the cloud? One of the example is 5G, but that's not the only example. So to start with, our instructional objectives. What are you going to cover in this session? So now first start with foundation of cloud computing. So it's, I would say, used as a buzzword sometimes as a business case study, sometimes as technical case study. We are going to mainly see the technical side of a cloud. Okay. So the business side could be, you can go and start selling your services in a cloud, and you can say, okay, my applications can scale 10 times in 3 seconds. That is a business proposition. But when you go for technical proposition, you need to talk about, okay, what technologies are we using? And as a, say, computer science graduate, that's what expected from you. Okay. We will see what makes a cloud, and that would be these two technologies. From the structural side, means how the cloud is built. That would be software-defined networking, or SDN, and network function virtualization, or NFV. These are two standardized technologies, and they create the cloud. Now, once the cloud is created, the infrastructure is there. Now you need to deploy applications on top of it. And that's the functional side of a cloud. And this is what we call cloud native. So what makes an application compatible for a cloud? That's what the functional side of a cloud is. And then we'll see some use cases that, okay, where these clouds are used. So one of the example is this 5G service-based architecture. which is a cloud native architecture. Okay, so when you use a 5G, it's a cellular system. So when your phone connects to the 5G network, behind the scene, any operation that you perform with your phone, let's say when you travel in a train while streaming a video, you go through a process called handover. So when you change cells, your streams get switched between cells. And behind the scene, there's some cloud computing application that runs and that does that switching. So we'll see some example of cloud native services which are inherent in a 5G system. Okay, so with that, we are going to start with the basics of a cloud. So cloud computing is an evolution of distributed systems. Okay, so for example, in a graduation in a level, you are, let's say, studying computer science and you are mainly focusing on centralized systems. Okay, so all your programs would run the same computer. When you see operating system, networking, that tells you how would you run an application, but in a single computer. If some of you choose to do a master's, you will be theoretically studying what happens when the application is too large to be run on a computer. So you need to distribute the application into multiple computers. And that's the concept of distributed systems. So what we do, we cluster a set of computers through networks and we deploy applications in all these computers. And how do you manage it? That's the notion of distributed system. Now, over last like 3 to 4 decades, distributed system has evolved as a concept. Initially, it was called grid computing, then cluster computing, and then cloud computing. So what cloud provides is the first part, which is distributed on-demand pay-as-you-go access. So distributed because applications would run in multiple machines. On demand means you will get the application whenever you need. You don't need to install the application. And pay as you go, you only pay for your usage. You don't need to reserve resources. If some of you have used AWS or any other cloud services, you know that your billing is based on for how long you would use the service. Same as this newer example of GPTs, ChatGPT or any other, generative AI tools. If you use their APIs, you will be charged by number of tokens. So access to what? Access to physical resources. And these physical resources could be compute resources like CPU memory, networking resources, which is basically throughput and latency. So you can say, I need a network of 100 Mbps of bandwidth, and it should not be exceeding more than 5 millisecond of latency. Plus the storage. I mean, slow storage for mass storage, let's say video applications, or a high-speed storage for database applications. So all these infrastructures is somewhere in a data center that you don't know. You as a client, you don't know. And there's an abstraction between these physical infrastructure and the client, which is the cloud itself. And this communication is served over the internet. Sometimes we use the term OTT, the OTT platforms we say. So it's over the top of the internet. Okay. The whole point of doing this is to reduce the provisioning overhead. So you don't need to buy servers, install operating system, hire engineers to kind of do the configuration for you before you run the application. The whole infrastructure will be provided to you over the internet. And therefore, the advantages are you would be virtualizing the infrastructure, so you don't need to physically buy it. If your demand increases, your infrastructure should scale. Take a look of the use case of Pokemon Go. It was a game that came, and that was the first example of an application that scaled so much because the user base increased suddenly that the hosting system failed. So that is a case study which is taught for Kubernetes, that you need a system that can scale up and scale down as a demand increases or decreases. This feature is called elasticity. So as you put more demand in a system, the system should scale up. As the demand goes down, it should scale down. So you'll be only charged about the amount of resources that you use. So For example, in AWS, the computing service is called EC2. That EC stands for Elastic Cloud. So the cloud lets you scale up and scale down on demand. The way it is done is a technology which is ingrained in Linux called namespaces. And we'll see some of this example in the lab. So what namespaces do, they isolate processes. Okay, so if you run a process in a namespace, that process doesn't see anything outside the namespace. And it also helps you to automate things. And this is sometimes in a business term called zero touch provisioning. So you bring a hardware, plug it in, and that's it. All the configurations will kind of execute with a single touch of a button. And we're going to see one of that example today with Docker. So you just onboard the application by one command. So forget all these commands and stuff. And the very end, you see this all in one command. And here, 3 scripts are going to run one by one. So they're chained command. There are 3 scripts, unrun.sh, build.sh, and run.sh. And they're chained with these ampersand symbols, means if the first one runs, then the second one runs, then the third one runs. So first is unrun, which is uninstalling if there's an old copy. Then you build the application from scratch, and then you run the application. So this is an example of zero touch provisioning. You don't need to install Python, or it's a Python application, by the way, or any prerequisites. Everything will be done through these scripts. And there's some business advantages. For example, this economy of scale feature means when you need more resources, you'll be given more resources, and therefore you'll be charged accordingly. On the other hand, what it also provides is called the service-based architecture. This is something I'm going to emphasize a bit. So this is a philosophical change. Instead of building an architecture and looking for applications, you first look for the application and then build the architecture. That is what is called the SBA, or service-based architecture. And over last couple of decades, with the rise of DevOps, this setup or this architecture is found to be the most effective architecture for large-scale software design. Right. So what are the different types of clouds are available? Mainly 3 types of cloud: public, private, and virtual private. Public clouds are those which are hosted over the internet, like AWS, GCP, Azure, these services. And the idea here is you don't need to pay a single penny to maintain the cloud. You just pay for the services you deploy on the cloud. Private cloud is useful when your data is sensitive or you don't want to share your application with others. It's a private application. Then you might set up a cloud in your campus. Now, please understand, private cloud does not mean running application in a local server only. Cloud computing has all the features I just mentioned: elasticity, multi-tenancy. Is that node running in your campus or on-premise, or is it running somewhere over the internet? There's certain legal restrictions sometimes that, for example, I live in the UK, so if I had to store something in a cloud, that data should be contained within the boundary of the country. Similarly, for other countries, there are rules like that. In India, I believe the similar Data Protection Act exists, where the data does not leave the border. There's another example called virtual private cloud, or VPCs, and this lets you create a virtual infrastructure over a public infrastructure. So you go to the public cloud infrastructure and create a VPC there. So basically what you do, you reserve a large chunk of resources, and within that large chunk, you can play with your scale up or scale down, but you pay for that entire reservation. That is what virtual private cloud is. It's normally useful when, let's say, you are a VPC provider and you first go and buy a lot of resources from, let's say, AWS or Azure, and then you subcontract those resources to the client that comes to you. So you manage the cloud for them. That's the example of VPC. So some of these, usefulness of private clouds. One is this cost prediction. So because it's running on your campus, you know how much you have spent, so you have a full control on the cost instead of running in the internet. Otherwise, you might be billed. Let's say you let a very high performance VM running in a cloud and you forgot to stop it. You're going to be charged for that until you stop it. So those issues don't arise when you go for a private cloud than a public cloud, but it also has its limitations. A middle ground between private and public is called hybrid cloud. So hybrid cloud is more of you break your applications into two categories. The private part of the application, which you don't want to share, it stays in your campus. Okay. And the public part of your application that goes to the cloud. So that begs a question that how do you break an application? It is easy to say that, okay, so you break the large application, small services, and you just, segregate them. What is the backend technology that does it? This is the main idea that we're going to go through in this session, that how to design an application in such a way that it becomes highly modular. The rule of thumb for a good software design is it has to be highly cohesive and loosely coupled. So the loose coupling means your modules would only communicate between themselves when it is absolutely required. Okay. And highly cohesive means applications or modules which would interact very frequently, they're going to stay together. So this segregation, we will see how can we actually build applications like this. So the one that I showed you, the client server application, there's a client side and a server side. The whole purpose is taking this application and breaking into two components, and we can put these two components wherever we want. The client should only know what IP address and in which port number the server side of the application runs. Cloud, and the main idea of hybrid cloud is separation of concern. What I just mentioned, that you take the application, break it down in two parts, and then you kind of separate that which part requires more security than others, and then you put those parts in a private cloud and rest goes to the public cloud. That makes it a hybrid cloud. So cloud services are normally served in three layers. The bottom layer is called the infrastructure as a service, which provides you the actual infrastructure where the application runs. On top of the IaaS, you run something called PaaS, or platform as a service. And in platform as a service, it's more of the operating system and virtualization layer. Okay, so you don't directly access the hardware. Rather, you have a virtualization layer in the middle through which you access the hardware. And then comes the SaaS, which is the software as a service, and this is the actual application. The way I would like to kind of present this is, for example, you are learning, let's say, DTP or any other tools, let's say Photoshop tools or any other tools, and you want to play with that tool, and you have at the moment nothing. Where would you start? You first go to Amazon or a computer store and you buy some hardwares, memory, CPU, motherboard, cabinet perhaps, and this will create the infrastructure for you. Okay, you're gonna assemble all the hardware, hard drive, memory, CPU, everything. But would that be enough? Can you just install the hardware and run the application? Of course, no. You need an operating system. This operating system will sit between the application and the physical infrastructure through which you're going to run that application. And then after the installation of the operating system, you install the application on top of it. So think of, if that example gets scaled to the internet scale, then the infrastructure as a service is the bottom layer, which is a prerequisite to run a platform on top of it. That will be platform as a service. And once the platform is there, then you can run the application on top of it, which is software as a service. So for example, if I open Google Drive, this is an application I'm running. Behind the scene, there's some kind of operating system that is supporting the application. And behind the operating system, there is a set of hardwares. So these are three layers in which cloud services are kind of served. Now, which particular layer you will be served with, it depends on what is the purpose of your application. So this is a very high-level depiction of these three types of services and responsibility of the application provider. So let's see if you want to run everything by yourself. On the left is a pre-cloud computing era application. And here you start with the data center where the physical infrastructures are. On top of that, you have networking setup, storage, servers, and these are the physical stack, what we also refer to as bare metal stack. And then we put virtualization on top of it. So we can club multiple physical infrastructure to create a single pool of resources. Then we put an operating system on top of it, let's say Linux, and then a database for storage, security, obviously, and then the application. So now, for every single layer, you need to have an engineer. You need to have one guy who would be doing the data center bit, one for the networking, one for the storage, one for the servers, and then at the very top, you have the developer who will be working on the application side. So if you think about just to run the application as a provider, you have to pay all these people. Okay, so that makes your cost of running the application much, much higher. Compared to that, when you move to IaaS, then the cloud providers say the data center networking, storage, server, virtualization is our responsibility. Okay, you come with your operating system, database, security, and application. So you only need, let's say, 4 engineers or 4 types of engineers to run your application. If you move to PS, then it's only the application that you need to maintain. So you only hire developers. Now, if you go to SaaS, then it's completely offloaded to someone else. So as you can understand, when you move from left to right, you are losing autonomy, but with a gain of, let's say, less cost for running the application. So it's really based on, let's say, what application are you running and what are your requirements. Based on that, you choose what model to go for. Okay. And once the application is onboarded, then a cloud client would communicate with the SaaS application, and it's the cloud client through which the user will interact. So when you interact with application, let's say YouTube, you are actually using the cloud client, which is a YouTube app. And behind the scene, there is a server where this app is being hosted, and that server is specific to the customer or the user because it holds the history of the user. So that is how applications are hosted in a cloud. Before I move on, any questions?
Sir, how the SaaS actually, you said that infrastructure we project provider manager, these do service in platform, this only application we have to run, and in the SaaS all are done by the cloud. So what then, how, like, how we actually do this, like how we actually come to this SaaS part?
Okay, so think of you are a small startup, okay, and you have an application or you basically worked on an algorithm for, let's say, a number of years, and you have come up with a very efficient algorithm that does something amazing. That is the algorithm behind the application. Do you agree?
Yes, sir.
Okay. Now you don't have the funding to maintain the rest of the stack, data center, networking, storage, and all that. So instead of hiring like 10 engineers, one for each layer of the stack, you hire 10 developers, and all of them will be working on the application. Okay. This is exactly what these startups would do. Once it is done, then the application will be placed in a cloud, for example, the SaaS application. And then think of this startup is consulting for a business firm. Okay, so instead of you come up with the business problem, a business comes to you, say, I want an application that does this. And you hire 10 software developers who develop the application, and you create the application for the business. Now, question is, would the customer be the customer of your startup or the customer of the business? First, answer this.
So the customer would be of my startup.
you are the consultant. You have built the application, you have the algorithm in mind, and you have built the application that solves a business problem. The business problem comes from a business entity which doesn't have the expertise to build the application. So that's why they come to you for consulting. Agree?
Yes, yes.
So the customer comes to the business comes to you as a client, you provide the application to the business, and that application will serve the customer of the business. Yeah.
Yeah.
So you are the developer who developed the application, you onboarded the application in a cloud, that application solves a business problem, and that business serves to its customer. That customer has the cloud client, and the business customer uses a SaaS application to get served. Yeah.
Yes, sir. Yes, sir.
So as a consulting firm, you won't be building just one application. You might be specialized in building a specific type of application. So think of example like Zomato or Swiggy. They have their own application backend. So they have their own engineers to build the application. But that can also be done by, let's say, a freelance engineer who would build similar food delivery application for, let's say, small entities, small restaurants. So the restaurant's customer would use your application, which you have built as a consultant. So that's what the migration from PaaS to SaaS is. Once you load an application on a PaaS, it becomes a SaaS application. And then that SaaS application would serve a business customer.
Yeah.
Okay.
Thank you, sir.
Okay. Any more questions? Moving on. So what makes a cloud? What are the ingredients of making a cloud? So there are mainly two technologies. The first one is called software-defined networking, defined in the 2015 RFC 7426. If you are not familiar with this term RFC, it stands for Request for Comments. So, for example, for any country, we have a constitution and laws. And whenever we kind of cite a particular law, we go, okay, so this section, that subsection, that clause. Similarly, for networking or industrial grade, engineering, there are some kind of references. For networks, this is called RFC, Request for Comments. This is maintained by IETF or Internet Engineering Task Force, which gives you the definition of something and how that particular technology would work. Any operator would use that definition to build their application based on those concepts. So SDN is a concept, software-defined networking. If a random company comes and build an SDN application, it has to comply with whatever is defined in that particular RFC. Another building block for cloud is called NFV or Network Function Virtualization, which is an RFC 8568. So if you just Google RFC 8568, you would be getting a text document where what NFV is and how it should be built. They're all defined. So basically, SDN is a three-layer stack. It starts with infrastructure, then control, and then application. So infrastructure means these are the forwarding devices. Think of switches. Traditionally, if you would buy, let's say, physical infrastructures for forwarding traffic, switches and router would be your devices. That device would have three layers of operations. At the very bottom, you had something called forwarding plane, which is capable of forwarding traffic. How the traffic would be forwarded, that would have been controlled by the application plane, the control plane, that would run the algorithms. For example, if you're deploying a routing protocol, let's say RIP, then behind the scene, there's a Bellman-Ford algorithm running, okay? And that would run inside the router. And then you have something called a management plane through which you access the router. One box having all these three layers. But as we move on to more distributed systems, what happens? These layers, they get disaggregated. Okay, so you only buy switch, which are dumb. They don't know what to do. They are told what to do by a server which runs the control plane. An application on top of it that tells the server that, hey, I want, let's say, a route from point A to point B that would give me certain amount of bandwidth and it should not exceed certain amount of latency. The job of the controller is to go and look for that path in the topology and give you that path. So this is the basic from which this agility that you get in the cloud that comes. And the lower layer is for forwarding, the control plane is for policy, and the application plane is for the network applications. Now, when you have these three planes, what you can also do, you can use virtualization on top of it, by saying, let's say your device that we are saying, the infrastructure device, they are not physical router or physical switches. They are all virtual router and virtual switches. So they are basically virtual machines running an operating system, which is a router operating system. Now, once you have these hypervisors installed and you scale your application and you scale your infrastructure, then you need some kind of a management, right? Because let's say you are running a virtual router in a server, and for some reason that server failed. Now, what happens to that router that was forwarding traffic? It needs to be migrated into an active server, right? So don't expect that it to be done by a human. It cannot be scaled if you do manual migration. So you need an automated way of migrating tasks whenever it is needed. This technology is called MANO. MANO stands for Management and Orchestration, which is also a standard. It is a standard not from IETF, so it doesn't have a RFC. It has something called ETSI document. ETSI stands for European Telecommunication Standard Institute, and they are also responsible for standardizing certain standards. So MANO comes from ETSI, and these two, NFV and SDN, comes from IETF. So all these three layers, as I mentioned in the SDN, they would be migrated into a virtualization layer. And then these components would be called a virtual network function, or VNF. And managing this VNF with a MANO altogether is called NFV. So don't get confused with these two terms, NFV and VNF. VNF is the entity, NFV is the concept. Okay, so let's move on. And there's some links here if you want to know more about it, that actual documentations which are linked in this URLs. Now let's come to the cloud native. So you understood what a cloud is, different layers of cloud, different technologies which makes up a cloud. Now we move on to see what a cloud native technology is. So cloud native is, first of all, a design pattern. Design pattern, if you are not familiar with this term, it is the set of rules which is followed while designing and developing an application. It depends on what the requirement of the client is. Okay, design pattern for a mobile application is different compared to an application that is served over the cloud. Design pattern of application which requires a lot of bandwidth, but it doesn't need a lot of quality of service requirement, is different compared to an application which is very, very time sensitive. Okay, so design pattern tells you how would you run or design an application. So there are a couple of things that make a cloud native applications, and they're all concepts, and these concepts are realized through different techniques. The first idea is called a microservice. So a microservice is basically breaking a large application into small services. Again, the same idea of highly cohesive and loosely coupled application. So each of these modules of the application would be called a microservice. We would assume that each microservice would contain n number of highly cohesive applications, or the module of the applications, and then each of the microservices of the application would be loosely coupled. Okay, you will see a real example when we'll see the application that we are going to onboard with Docker today. Now, microservices are logical entities. It tells you how applications should be broken down into small pieces. The actual way you break down applications are called containers. So containers are packaging systems in which you run codes. Okay, I believe most of you, when you run applications, you write a script, let's say in C, Python, whatever language, and you run it through a Python interpreter or C compiler. This is called running natively. So you are using your computer, physical computer's hardware to run the application. But what containers do, package this application into a packaging or encapsulation called a container. And what it gives you as a feature is platform independence. So while building the application, you don't need to worry about that what the target environment is and whether that target environment would be compatible to the application that you're building. So you don't need to worry about whether that target environment would be having certain libraries installed without which your application won't run. Those issues will never occur if you package applications in a container. We'll see those in the hands-on, that how exactly this is done. The next thing is scalability, as I mentioned. So when your demand increases, you also scale up your application. Now, at some point, you'll feel that when these applications are, when your application architecture becomes highly scalable, each of the component of the application, like microservices, they scale differently. Okay, so in real world, when application scales, the example that we use is not an inflation. It's not like inflating a balloon. It doesn't scale uniformly. Sometimes a part of the application scales differently than the other part of the applications. So you need some kind of a management that scales these microservices independently. Okay, again, the whole objective is to lower the cost. So instead of scaling the whole application, it's better to only scale the part of the application which requires scaling. This is called orchestration. Okay, this is something we're going to cover in the next session. This is where Kubernetes will come. And this entire process has to be automated. CI/CD, okay, continuous integration, continuous delivery. And this will be done by a tool called Argo CD. We will do the next class that would achieve something called reconciliation. So automation and orchestration, these two parts we will skip for today. We'll mainly focus on microservice, containers, and scalability in this session. More information, go to the CNCF GitHub page, and you can find the actual definition of these ideas. So what I just mentioned are here, loosely coupled application which are interoperable. So you can move between clouds. You don't need to worry about whether the baseline would match or not. So yeah. Microservice architecture. As I said, the microservice architecture is the basis of breaking down an application into small services. So the idea was this: when software development, started back in 90s, the architecture that people would use was called monolithic architecture, or nowadays we call it monolithic architecture. Means you would have a single application, all its files, and an executable. The problem is you can't take a subset of the feature of the application and you can port it to a different application. So this reusability was not a thing. Now, as the growth of the software industry, scaled and different requirements starts coming, people realize that this waterfall way of building application is not going to scale anymore. So therefore, the software engineering discipline, they moved into a domain called agile. You build, fix, then again you build and fix. This incremental model of software development. And that's what you see nowadays. Nowadays, if you want to use, let's say, an Adobe product, Photoshop or any other tool, you never own the application. You only subscribe to the application. So basically, no matter how many years you pay for the subscription, you never own it. So the application always runs in the Adobe Cloud, and they incrementally add features in the application, and those features gets unlocked to you based on the subscription you go for. This is an example of microservice architecture. So instead of having a single monolith of all the components together, now they are broken down into smaller pieces. So now a part of an application could be repurposed for a different application because they are loosely coupled. And you can take each of these module and you can sort of reuse it for other purposes. So that is what a microservice architecture is. As I mentioned, microservice is not a physical or a logical entity, it's a concept. Based on this concept, we kind of break down applications, and that breaking down is done through this technology called containerization. Right. So what is a container? So containers are basically packaging format of an application. Now, I believe the best way of explaining container is a bottom-up approach. So you start with, let's say, if you get hired in a startup today, and they give you a task that, okay, we need to first set up our stack. Where would you start from? Okay, given that you have the hardware with you, you have the servers and networking components with you, and normally you had an IT engineer who would come and kind of plug all the switches and routers and the power, and that's it. Now it will give you an infrastructure from which you start. So let's start with that. Okay, at the very bottom, you'd be having the computing and the networking infrastructure, what we call bare metal or physical hardware. This is the first layer of the stack. On top of this, for each of these servers, you're going to install something called a hypervisor. Now, hypervisor is a generic term. If you have used softwares like VMware Workstation or VirtualBox, these are examples of hypervisors. Now, there are two types of hypervisors, type 1 and type 2. Chances are mostly you have used type 2 hypervisors, which basically runs on top of an operating system. So let's say if you do it in a computer, you have your physical hardware as your computer, you have an operating system running like Windows or Linux, and then on top of it, you install VirtualBox or VMware. Okay, so that hypervisor would require your operating system's kernel to communicate with the physical hardware. Because you won't be doing only hypervisor job in your laptop, you'll be doing other things as well. But in case of servers, that's not the case. The sole purpose of a virtual infrastructure is to provide virtualization. So therefore, type 1 hypervisors are one that comes with its own kernel. Okay, so example of that would be VMware ESXi. This is an example of a type 1 hypervisor. Proxmox is another type 1 hypervisor. So these are examples where your hypervisor has a kernel with it. So it is the operating system, but the sole purpose of the operating system is to provide hypervisor as a service. What it actually helps you to do, because hypervisors goes in individual physical computers, but that's not what you need. You want to kind of plug all the resources together to get a single pool of resource. And that is what you call a hyperscaler. So for example, if each of these computers have 1 terabyte of hard drive, let's say 10 cores each and certain amount of memory, the hyperscaler would be a pool of resources of, let's say, 3 terabyte of hard drive and 30 cores of CPU and the sum of the memory of each of the individual computer. On top of the hyperscaler, what you create is called a virtual form factor. A virtual form factor is normally classified in two classes, virtual machines and virtual networks. So the job of the virtual network is to provide networking virtually between the virtual machines. And inside each virtual machine, you'd be having a virtual hardware inside, a guest operating system on top of it, a runtime on top of the operating system, and the application. So when you run an application in a virtual form factor, the application would use its runtime to run on a guest operating system on a virtual hardware that will be enclosed in a virtual machine. Those virtual machines will interact with each other through a virtual network. All this infrastructure will be provided by a hyperscaler on top of a cluster of physical servers. This is the first thing you do to start with. But you might say, where are the containers in this picture? Okay. that will come afterwards. The problem if you run application in this way is, I'm sure that in operating system we have heard about context switching. So think of this. Behind the scene, there is just one set of CPUs running in the physical hardware, which is actually running the code. Okay. Now, if you have hundreds of VMs on top of it, then each of the VM would be running an application or multiple applications. And then the instruction coming from the application requires one level of translation for the virtual or the guest operating system, and then the second stage of translation in the physical layer. Now, as the system will scale, the amount of context switching in the physical kernel would massively increase. And we know what happens when the context switching reaches certain critical value, your system crashes. So this is not a scalable way of running application. This was the scalable way of running application when the amount of dynamics that we face in the cloud today was not there. Okay, 10 years back, that was the standard. But now we are moving to the microservice era where we take this application and we put it into something called a containers. So with this background, I believe now we are able to appreciate what is the meaning of a container and why should we use it. So in a container, what happens? This guest operating system is eradicated. We don't need that. We assume that there is just one operating system, which is Linux. Why Linux? Because Linux has certain feature in its kernel. I will not get into details about these features, but just the names of the features. First is called Chroot, CHROOT, then C group and namespaces. These are features which were introduced in Linux kernel version 4, and they let you sort of create what is called a Chroot jail. A prisoner in a jail, he sits inside that small jail, and that's his world. He doesn't see what's happening outside. Now think of, with that analogy, when you run a code, that code doesn't see anything beyond what restrictions is allowed on top of it. So this is the example, or this is the backend technology through which containers run. So when you run an application in a container, you kind of jail that application by giving certain privileges and restrictions. Okay, you will see more prominent example with the hands-on. On top of these, you run something called a container runtime. And this is a third-party tool that will take advantage of these features, Chroot, C group, and namespaces, that will isolate the application from the other application. So if you are a client running an application, you would be having your own private space, and you won't be able to see the other clients who are sharing the same hardware and what they are doing. This security feature is called multi-tenancy. So it's just like a tenant. You are renting, let's say, a room of a house, and that's your world. But there are other rooms in the house which you don't have access to. Okay. And on top of this container runtime, we create containers. The runtime of the application, which is a library and packages for the application, would go inside the container, and the app will go inside the container. So instead of an application running with this on a virtual machine, which requires you to translate the instruction one in the virtual operating system and then the physical operating system, is no longer needed. Instead of creating two different kernels, you are creating logical partitions or jails in a single shared kernel. This is the idea of a container. And we will see an example of this container through Docker. So container runtime is, nowadays we need to describe it as a separate entity, but Docker is the first example of a container runtime, or I should say the most popular example of a container runtime. But nowadays there are other container runtime like Rocket and CRIO. So therefore, it's not a one-to-one map that Docker is the only container runtime. There are others, but over the time, people like me who started like 5-6 years back with containerization, we are so practiced with Docker that we prefer to go for Docker-based container runtime. But just for sake of clarity, it is not the only runtime. So these microservices, as I mentioned, logical microservices, they are basically physically are containers. Physically means you can actually see them running. Okay, they exist. Containers do exist. Microservices are conceptual. Instantiation of a microservice is a container. That's all you need to understand. Okay.
Sir, as you said that in the virtual formation or there is a context switching, and how it struggled to translate the law in physical kernels, and how in containers we have the single kernel Linux, which have all of this. So, sir, if we run a container, so isn't that like Linux will take more space or something like that?
Okay, good question. All right, so it's not the space, it's the memory. Okay, process is a program in execution, so it's not the storage, it's the memory. Yes, it will consume some extra memory because you need to manage the application, but that memory that you extra consume is a fraction of the kernel. You see what I mean? Instead of having a full kernel for every single application, you only use a fraction of the kernel for the application. So yes, you'll be using some extra memory, but that sum of the memory is even lower compared to if you consider the whole kernel. So yeah.
Yeah, so like Linux use an instance of itself for different applications so that they can run in the container.
Okay. Yes, not fully. Okay. How many of you are familiar with inodes in Linux?
Sir, I don't know.
Okay.
I'm not familiar.
You know the Linux directory structure, right? You have different directory. Okay. So behind the scene, Linux maintains a red-black tree for that directory structure. So you do the tree command to see that red-black tree. And this tree has nodes. You know that data structures tree has nodes.
Yes, sir.
These nodes are called inodes because they carry a particular identifier saying this is where my position is in the context of the full directory structure. Now, when you, for example, do pwd, you basically see the string version of that inode. Now think of it, when you are inside a directory, okay, and you don't have the privilege to come out of that directory because you don't have access to the root directory perhaps. So your visibility is only restricted is what is inside the directory. Agree?
Yes, sir.
Now think of, just like this directory structure, there's also a process tree. Okay, the root process is in it that starts all the other processes. If you think of a similar restriction is applied, that a particular process with a given PID is spawning some children processes that runs beneath it. But that process is also got spawned by some other parent process, right? What if I only maintain pointers downwards? So this process will not be able to see anything that happened, above it. Do you agree?
Yeah, so it's like an encapsulation rather than instance.
It is. I won't use the term encapsulation because that has a different meaning. It's more of like it's a constraint. So every process maintains a child pointer. It doesn't have a pointer to its parent. So it doesn't. It cannot traverse back to its parent. So it's only visible. So the processes that are spawned from a given process are only visible to the process. This is the concept of jailing. Okay.
Yes.
Some of you might know that with Android phones you can unlock the root. Some of you might know the same thing for Apple is called breaking the jail. This is the reason we call breaking the jail, because it's the chroot feature that we disable. So now you can access root features from your phones. So that's the idea. You have a cap or a constraint that Applications don't maintain a pointer to its parent. It's only the parent who maintains pointers to its children. Okay?
Okay, sir. Yes, sir. Thank you, sir.
So it's not creating a virtual copy of the whole kernel, but giving restriction to the application that what the application can see and cannot see. Okay. So we will see more about namespaces in the next session when we actually deploy it in scale in Kubernetes. So hang on till then. Some examples of some benefits of having containers are portability, speed, scalability, things that I mentioned already. Okay. Now we are moving towards the hands-on. Okay. We will create the Docker containers of the application. So let's first start by understanding this life cycle of a container, from which it starts and how it is deployed. Typically, in any software development industry or any software development environment, you have two major environments: a dev environment where the engineers write their codes, and a target environment where the applications run. These two environments are breached by something called a version control. Shomojit has already taken the session, so you know what a version control is. GitHub is an example of version control that use Git as the version control in the backend. It starts from a source code. So you write a script in any language, C, C++, Java, Python, doesn't matter. These source codes are the actual code that will run. Okay, but we might not be sure that whether the target environment will have all the dependencies installed. So therefore, a classic example in the old days, we used to install .NET framework to run certain applications. That .NET framework would install all the additional Windows components that would be needed for running the application. Now we don't need that dependency anymore. What we will do, we'll put the list of libraries we need with the source code, and we package it into a file called Docker file. This is a file which will refer to the source code directory and the code and the prerequisites for running the code that we assume it stays in the directory. We will run this Docker file, and this is called a build mechanism. And from this Docker file, we'll create something called a Docker image. In general, after building something, what we get is called an artifact. Okay, so Docker image is an example of an artifact. Then this artifact will go to a registry, and the source code will go to a repository. So what I showed you somewhere here, I think, yeah. So this is a repository. This is not a registry. This is where the source code lies. So you can go to the app and you can see client and server, and you can go and take a look that there's a Python file, and you can see the source code. Okay. So that goes to the repository. The Docker image, which is a built version of the source code, goes to a registry. Okay. In cloud, we don't install applications. We deploy applications. These applications are deployed through these artifacts. So we don't need to install anything. We assume that this image will have all the requirements inside it. Just recall this image. Your libraries and packages are all encapsulated inside the container. Okay. So this artifact, when it is required by the target, it will be pulled down from the registry. So Docker image was pushed to the registry from the dev side and got pulled into the target side. But Docker image is just like a file. It's a file itself. When you run this image, it becomes a running container. Okay, so build, push, pull, run. Yep. Now running containers live in a memory. If you want to save the state of the container, you save it. It again becomes an image. If you want to stop the container, then you stop it it becomes something called a suspended container. If you want to restart it, it restarts or resumes from its suspended state. So a suspended container is something like it lives in a swap memory. So it is not an active application, but it is not something which is killed. If you want to kill it, then only it get removed from the memory. This is the life cycle of a container. So you start from a source code, you refer the source code in a Docker file, you build the Docker file and you get an artifact called a Docker image. That image gets pushed into the registry, and you can also maintain the source code in the repository. This repository will be completely hidden from the customer side or the target side. It will never get access to the physical copy of the code. You could see my code because I have put my registry public, so you could see it. Otherwise, you won't be able to see it. What you will get access to is this registry, and then you pull the image from the registry. Then you run the image. It becomes a running container. Stop, start to pause it or resume it, and then you kill it. This is also similar to what if you have done Java threads. It's similar kind of a life cycle model. So, any questions before I move on in this life cycle, because we're going to actually see hands-on on this.
No, sir.
All good? Okay. The following slides I will skip because this is things for the next session. Okay. A quick gloss over what's coming. So in today's session, we are going to kind of encapsulate our application into containers. So we'll see this life cycle in action. In the next class, as I mentioned, the requirement of Mano is when this number of applications start scaling, it becomes difficult to manage it. And especially when an application, doesn't scale uniformly. So for example, what if the server side doesn't scale, but the number of client shoots up? So you need to somehow scale the client part of the application more compared to the server part of the application. This is something you cannot do with Docker because Docker was never built for it. Docker's job is to just containerize your application. That sort of a control is called orchestration. And this is done by Kubernetes. So in the next class, we'll create something called a Kubernetes cluster, which would be having a controller node and worker nodes. And then these applications that we are going to containerize today will be encapsulated into a form called pods. Okay. And this is the way Kubernetes sees modules or microservices. And then we will actually go through this process of building a pod from scratch. And then we see an example, like where can we use it? And an example of it would be a 5G system. Okay. So these are all coming in the next class. And as you can see, the number of slides are far less compared to today because next lab would be much more hands-on heavy. Okay, so we have seen the Docker lifecycle already. We're now moving into, let's say, actually seeing what a containerized application looks like. So I will be using this tool called draw.io. This is where I'm going to draw something to explain what's going on behind the scene. So it will also give you a reference how things are connected. Okay. Okay. Now to begin with, I have a server running somewhere in the cloud, which I consider as infrastructure as a service. Okay. Going back to our example of IS, we have some kind of infrastructure that has CPU and memory that I have access to. I am sitting here. So this is my laptop. Okay. And I have internet in the middle. And what I have done is I have set up something called a tunnel from my laptop to a VM that is running on top of this infrastructure. Okay, this is very, very important. You understand how the existing setup looks like. So when you replicate in your side, you know how to do it. Now, in my case, because for some reason I don't run application directly on my laptop, I am using this internet as a tunnel to communicate with the VM. In your case, you could just create a VM in your computer and you can access that VM using localhost. So that internet thing will not exist, but a logical connection between the application, your laptop and the VM would exist. Okay, so this networking bit doesn't matter if you do it locally. Okay. On top of this VM, I am running Ubuntu, I think 24.04 LTS. This is an operating system. So Ubuntu is a distribution of Linux. 24.04 is the version. And LTS stands for long-term support. So normally Ubuntu has two line of supports. One is long-term support, another one is incremental support. Long-term support means if you use this VM, it will give you support to its libraries for the next 6 years. Okay, I think 6 or 8 years, but yeah. So normally when we install servers, it is preferred to use an LTS version. You could get these VMs or you could get these images if you go to releases.ubuntu.com, and here you will find all the releases of Ubuntu. And you can see there are versions from 14.04 to 24.04. Let's say I'm using 24 at the moment. So I go 24.04. Doesn't matter which subversion you use. Let's say the latest one, 24.04.4. And it'll ask you, do you need a desktop image, which comes with a GUI, or a server image that doesn't come with a GUI, but only the kernel. Obviously, for server installation, you go for the server image. And as you click here, it would ask you to download the ISO file. Okay, I have already downloaded and installed it in a VM, so I'm not showing you. Yeah. So this Ubuntu VM that I'm running, I have also turned on SSH to it. Okay. Yeah, SSH is a protocol, secure shell.
Yes.
It uses encryption in the backend, so you can remotely connect to a CLI, okay,
Yes, sir.
where your communication will be encrypted. So SSH runs in a client-server mode, so you must have a SSH client in your laptop. So I say SSH C, which is the client side of the SSH, and it is normally installed in any terminal by default. So except CMD doesn't have SSH by default, but PowerShell has SSH, or if you have any Linux terminal, it by default comes with SSH. And then there's a SSH server. So basically what happened, SSH gets served in port number 22. So if my IP address, so in this case, my IP address is 10.120.59.70. This can be different for your IP address of your VM, and it is served in the port number 22. And what happens? This SSH client needs to know this IP address, okay, and it needs to also know the username of the VM. In my case, it's user. So basically, user at the rate 10.120.59.70:22 is the socket through which you will communicate with the server. Okay, so this connection that I mentioned from the laptop to the VM is basically this connection. It's a socket-to-socket connection from the SSH client to the SSH server. Okay, now to use this, all you have to do is to take this string, which is user at the rate, the IP address, and then you say, I want to connect to this socket using SSH. Okay, this is a command you will put in your client side, and this SSH command will automatically go and look for the port number 22. So it will make the connection. Clear? And after that, you're going to ask you for the password, and you provide the password and you get access. So I think this is where we can start with. That much of setup is already there, and this is not a rocket science to build this at your side. Okay. Quick command reference. Sometimes after installing Linux, you might not get SSH running. So I'll show you how to check that. So I have a CLI running here. Good. So I'm going to open a new terminal, and I will interact with my server through it. I'll do some basic things first because I have a different environment running. So this is not necessary for your side. Okay. So you should be getting a prompt like this. Now, first thing first, I ping to my VM 10.120.15.9.70 and see if it is live. It is live. I'm getting response back. So all good. So I do SSH user @ 10.120.59.70. Okay, that's the socket address. So the IP address, SSH is port 22 TCP, and user is the username. Press enter. It will ask for the password. I'll type the password, which won't be prompted, and you will be welcomed by the VM. So now you see my prompt has changed. I have access to the VM now. I can verify that if I do IPA, I should see the IP address is the IP address of the VM. It is not the IP address of my local computer. Okay. Now, if you don't have SSH installed by default, so you need to access the CLI of the VM, perhaps using a VMware or some other tools which gives you access. First, check is SSH running in your machine or not. Okay, now let's see init.d and SSH status, and it should show you active. If it shows you inactive, means SSH is installed, but it is not running. So instead of status, you would say start or restart. It takes these 4 commands: start, restart, stop, and status. So you can start, restart, stop, or see the status. If it doesn't show anything, means SSH is not installed. So to install SSH, you do sudo apt-y installed open SSH server. So we are going to run the server in the VM and client in the CLI. So this command will install SSH server in your VM, and then it will open the port 22. Because you already have SSH installed and it's running, so you are good. Now, the first thing that we need to do is to see what this application actually, what this application actually does. So let me first take you to the repo. The first thing to understand how this application is structured, okay? And this is a typical way of structuring any cloud native application. So if you go to the repository, because I know you have already seen the basics of GitHub already, this is a repository, and this repository has only one branch at the moment. So the main branch is the branch that you expose to your customer. Okay. And this branch has this code base. It also has a README where something is defined. So if someone has no clue what this report does, there are some tutorials here. It also has a license that says that don't copy and make money out of this application. If you make money, then pay me. That's the whole purpose of doing a license. Unless you can just use it without, if you don't earn from it, it's fine. That's the idea of open sourcing. Now, in my main branch, I have a folder called app. In that folder, I have 2 subfolders, client and server, where the client and the server sides are written. In the client side, there are some folders, some files, and one main.py file. The main.py file is actually the backend or the backend of the client part of the application. It also has some other files One is requirement.sh. I mentioned that when you run a container, you also put what are the prerequisites to run the container. And for that, you need um, a set of libraries to install. And these are the libraries that we need. I'm saying that this application is built based on this library, FastAPI, UVCon, Jinja, Python multipart, and HTTPX with the given versions. So the expectation is before I run the application, these libraries will be installed. Okay. And then there's a run.sh, it's a bash script. The bash script says that I will start by taking an argument, the first argument, $1, and I'll put it in my port variable. And then I run this command, uvcon main app reload host 0000 port, then the port variable. You don't need to understand what this actually does. All you need to know, this is the command that runs the application. We are dealing with an application of type web app. Applications would not run as a Windows application. It will be served by a web server. UVCon is an example of a web server. So it will expose the application in the port number you specify here. So we'll pass it as argument, and it will not discriminate about any IPs from which the application is invoked. So this script, if I just do run.sh with the port number as argument, the idea is this will start the script. Now, obviously, UVCon is not a standard Linux command. So to have this, we must install UVCon using the requirements. Are we clear with these three files? Main.py, which is the actual Python backend, requirement.sh, which is the requirement, because if you go to the Python file, you see this HTTPX and all these libraries are imported. So they must be installed first. And run.sh is the one script that runs the application. The GUI that you saw, the HTML and CSS bit, it comes from the template directory. So this is a standard way of kind of organizing your stuff because I'm using this framework called FastAPI. It wants you to structure your code like this. And HTML is this index.html is the actual HTML design, which is something I don't want to go into. And if you have any JavaScript, because I have a graph visualization, so I use some D3 JavaScript, which is here. Ideally, these are the codes that you will be supplied with from the developer side. Okay. Now I mentioned about Dockerfile. Okay. So Dockerfile, if we go back to our slideshow here, so the source code I just mentioned, it is already pushed in a repository I just showed you. And I have now a Docker file, which I mentioned it will refer to the code base. Okay, so let's see how it is referred. Docker file is a text file written in a language which is proprietary by the Docker ecosystem. It has specific directives, which I'm going to go one by one. So Docker file is the manual through which you build a Docker image. A Docker image is an artifact that gets created from the Docker file. And this is the artifact that you can port into a registry and you can dump into the target environment. So any Docker image starts from a base image. Okay. I am using a base image called Python 3.12 Slim. This image is based on a very lightweight Linux distribution called Alpine. And on top of it, we have Python installed. So we don't start by installing Python. We rather reuse an image from the Docker Hub where all these images are stored that has Python installed. If you have an image which is not standard, means it's not in Docker Hub, which is not a very recommended way of starting a Docker file, then you have to specify the actual HTTP or FTP URL from which this file can be pulled in. Now, what we want is to add layers on top of the Docker file. So I will make a quick visualization here. At the very bottom, we have this Python 3.12 Slim base image. Then each of these commands, workdir, env, copy, and all this will create what we call layers on top of this image. This is what we call the Docker file system. Okay. So the first layer says that I will set my work directory in /app. So whatever the home directory you are in, you create a directory called app, and you will get into the directory. So the following commands will assume that you are in the app directory as your PWD. Okay. So that's the workdir. And you will see this in action when we run the file. And then we set some environment variables, these two, which is a practice, and I don't want to spend time on explaining that. You can just Google it. What do they mean? You will know. So if you have to set some environment variable for your script to run, for example, here there are two of them. That will go to the layer on top of the workdir. Then I'm saying copy the requirement.txt to dot. Okay. So this is the file, and this file requirement.txt is local to the Docker file. So when I call this file, it will see that the level at which the Docker file exists. Do we have a requirement.txt file? If it is there, then copy to my current directory. The current directory is the workdir. So basically, you are saying copy this file into the container. That is another layer. So a layer on top of it, and we put it here. Then we run this pip command. So in case you don't know what pip is Python installer for packages or something. It is a package installer for Python. Okay? Like apt for Linux or Ubuntu. So when we run this, what happens? We are saying run the command pip install no cache dir, means it will install no matter if you already have installed. So first upgrade the version of the pip to the latest version. If this command works, then we chain it with the next command, which is install from the requirement.txt recursively, which is -r. So it will go and see where the requirement file is, and it will go and see what are the packages and versions defined in the requirement file, and it will install it one by one. So therefore, the ordering matters. Just imagine what would have happened if you put this command before copying the requirement file. It couldn't find the requirement.txt, and hence it's going to give you an error. So Docker files are executed sequentially. So you need to make sure that the dependency is linear. So if you are using this requirement.txt as one of your command, it must be there as a preceding command. Okay. Once this is done, means I have all my runtime installed, all the packages are installed. Now I'm safe to copy my application. So the application is the directory itself. So static, template, and all the other things. You might argue, so okay, the Docker file is also part of the directory, so is it okay to copy it? Well, not okay, but it will not make any harm because this file will not be invoked by any of the commands. One thing that you can do, you can selectively say copy this folder, and these files. Okay, so we need everything but Docker file. There are other options. You can put a Docker ignore file, which is a hidden file, and you can mention which file to not import when we say copy everything into the workdir. So it will ignore those files which are listed in the Docker ignore file. Take a look of Docker ignore if you want to know more about it. So after the line number 13, we have the entire application copied into the Docker image. Now we get to the run module. So run chmod. This is the last layer that we are going to put. Not the last, but penultimate layer that we're going to put. So here we will say If we run this command, so you first make this run.sh executable, so we can execute it. And we know what's the content of the run.sh, which is taking a port number as input and running the UVCon with the port number. So it will make this application accessible. So now, if I go to the Docker file again, the next command is expose. Well, the idea is this. We will, so in this VM, we will host our application as a client server application. And the client server will have a client side and a server side. What we are now seeing is the building of the client. Okay. Now, whatever the IP that we are using here, the client will use a port number 9001 and the server will use a port number 9000. Okay. Question: as a customer or as a user, am I going to connect to the client or the server side?
Sir, client.
Right. So for that, because I mentioned this is a web application, unlike SSH, which is for accessing the VM, if I am a client, I will need another application that will communicate with the client application. So which protocol should I use to connect a web application? It's not SSH. What application is that, or what protocol is that?
HTTPS, I guess. The connecting web.
Right. I'm not using HTTPS because I haven't set up any RSA, but HTTP by default. Okay. So HTTP runs in port number 80. So basically what happens, there is a HTTP server which is being served by UVCon, and this server listens to the requests coming from the client side. Okay, so this is the web server, and my HTTP client, which is my browser, will create a connection from the client side to the web server, given a port number 9001, and the web server will redirect it to the client part of the application. So you can now obviously guess that when I give the port number for the server, it's the same HTTP or web server, which will forward the connection to the server side. Clear? So this connection is to access the VM. This connection is to actually access the application running on the VM. Number is 9001. So let me show you how did I configure that. First of all, I need to tell Docker that which port of the VM you should use. We know port is a 16-bit number, so it varies from 1 to 65,535. The first 120,024 ports are reserved for well-known protocols like HTTP, SSH. Port number from 120,024 to the rest of the port numbers are called dynamic ports, and these are used for the applications. So I'm using one of those random port number 9001. Problem is, in this stage, when we use Docker without Kubernetes, when we expose a port in the container, that ports get reserved from your physical host. Okay, so you cannot run any other application despite of being Docker native applications. They cannot use this port anymore. It will be reserved. And this is one of the example of this jail thing, that if I say in the Docker file that I'm gonna only use the port number 9001, then the application inside the Docker container will not have access to any other ports except 9001. So that's the restriction I'm going to put. We can also put other restrictions. For example, you can put how many CPU core that this container can get access to, how much storage, how much memory. So all these restrictions you can define in the Dockerfile. That will be a bit advanced. You can have a look on Dockerfile verbs separately, and you will know how to add those restrictions. And the
Sir,
same code, yes.
So I was asking that you said that if we expose this port, then the container, then whatever service running, it will only use that port. What if we don't mention it? Then what's the default port that it will use?
There is no default port.
So we have to mention it, right?
Yes. So the
Okay.
idea is, in network security, there's a principle called principle of least privilege. Okay. So you only give access to resources which are absolutely required. So if your application doesn't require any port exposure, okay, that's the bare minimum, right? Your application might not need any access to any port. So therefore, Docker doesn't give you any default port. Yeah. So
Yes,
whatever you expose here, it gets allocated from the operating system. So that port gets mapped to this container. And similarly, when I run the CMD, the last line, which is here, let me see if I put the other one. Sec. Okay. So this is another layer of command, expose 9001, and that would go on top of run. Set simply. Okay. These layers, all these layers, starting from this Python 3.12 Slim to expose 9001, think of they are all read-only layers. You can't make any changes once they're created. The only layer which allows you to make changes is the last layer. Okay, this is a feature of the Docker file system. Why is it like this? Do your own research, you know. And this is this last line. There are two commands what you can put as a last layer. One is called CMD, and the other one is called entry point. There's a very tiny difference between these two, but just to be as minimalistic as possible, using CMD. What CMD does, it will execute whenever you run the container. So if we go back to our lifecycle again, whatever you have seen as read-only, so all these layers from Python 3 to expose, they will stay static inside the Docker image. And when you push it, you pull it, it will be just like that. You can't change them. Once you run the image, basically what it tells the Docker, then run the last layer. And the last layer of the Docker container is either a CMD or an entry point. I'm using CMD, so just stick with this. And what the CMD command tells you, it takes a command line argument as a list. So command line arguments are normally identified as dollars. So $0 is the name of the application. $1 is the first argument. So the 0th position of the list is the name of the application, run.sh, and the first argument is 9001. Why so? If we go back to our run.sh, we will know the first argument that we are passing is the port number. So that port number will then be used to call the UVCon program to run the web server with the port number. So basically, what this Docker file is telling, that we build the image from a Docker file with all these layers. When we run it, you're going to call the run.sh file. You'll pass the argument, the port number. Then this program or this run.sh script will create a web server that would get access to 9001 port. So basically, behind the scene, beneath this Python 3.12 Slim, there is a Linux kernel. And this kernel, basically this is the kernel, and this container gets access to a jail created for this container on top of the kernel. So think of like this. like this. So this yellow thing is the jail, which is isolating this application in the kernel. So there could be other applications. And in our case, we have another application, is a server application that is going to also share the same kernel. So we can think of exactly same replica here. And if we go back and check the Docker file of the server, you should see a similar file, Docker file of the server. And it's exactly the same file, the same Slim application, the app directory, packages, and we copy all the files from local directory. Just here, the directory is different, the codes are different, but that doesn't make much difference in the Docker file. We make this run.sh executable, so you can execute it with this // command. Otherwise, use sh and then the file name. And the port number is different. So because the other port 9001 is already allocated, we are going to use 9000 for the server, and then you run the application. So basically, the only difference is here, which is 9000, and here, which is 9000. Yep. Now, behind the scene, Docker also does another thing, which is you see these two layers. Sorry, the first layer, Python 3.12. You see, this is common between both the containers. Okay. So what Docker does behind the scene, instead of creating like two copies of the same thing, it creates a container or creates an image of Python 3.12 separately. And what it does, it says, all right, so you know what? I have one copy of this, which I will let both these containers to share. That is an optimization that Docker does to save space. So in action, we are going to see this happening. So do you now realize this client and server, as I mentioned, is a logical description. They actually look like this. There are layers of instructions and Docker files. And if we have some layers which are common, that gets separated. Okay, and it lets the other containers to use it. All right. So if we go to the README of the repo, it tells you where to start from. Okay. So to start, we need to have a Docker runtime first, which will create all these layers of isolation. By default, Linux doesn't come with Docker pre-installed. So what you can do, you can go and type this command to install Docker. Let me show you. So what I'm going to do, I'm going to say sudo apt-y installed docker.io. This is not the full-fledged Docker, by the way. For our demo, this is enough. But in a production, there are different ways of installing Docker. This is just to start with Docker. Okay. And if you press enter and you provide the password, in my case, I already have Docker installed. So just in case if I want to just get rid of it, sudo apt-y auto remove and docker.io should remove Docker from my computer or my VM. And it'll take some time because my engine was running in the back. Okay, so everything is removed. And if I now say Docker enter, it will say, okay, I don't know what Docker is. It will also give you this example that way, how can you install Docker. So let's install Docker. Sudo apt-y install docker.io, and this will install Docker for me. And whatever it says, just say yes. Good. So now, after installing Docker, what happens? Docker creates a group called Docker, which by default you as a user is not a part of. So you need to make yourself part of that group. The command is sudo user mod. So you are modifying your user arguments, saying I want to add myself to a group -ag, and the group name is Docker. Enter. What's happening? And okay, so who is getting added? The user itself. So which is user as the variable. Now you have become the member of the Docker group. So by the way, this user variable is basically your username. Whatever username you put here comes here. Ideally you would have logged out from this CLI and restart the VM to make that group change effective. There's a shortcut of doing that. If you type this command new group Docker, it will kind of do that without restarting the VM. Now you are part of the Docker group. You can verify that by typing, first of all, Docker -- version to see if Docker is installed, and if it is installed, with what version is it installed. And second, you can type some Docker command to test if you can access the Docker engine. So one easy command to check is docker ps. And okay, I think I need to restart my VM. It didn't work as expected because I uninstalled my container. Give me a moment. Let me do a restart. Init. Before I do the restart, let me show you something. Instead of saying docker ps, if I say sudo docker ps, does it work? Okay, so I have to restart the system. Init 6 will restart my VM. I'm gonna wait for a couple of seconds till the CLI comes back. Okay. Okay, so I need to do a sudo before it. And we are now closed from the CLI, and we have come back to our, like, my laptop CLI. So the VM is now closed. I can do a quick trace. I can say ping to my 10.120.59.70 IP address, and I'll wait until my response comes back. That will tell me the VM has completed its restart and it has turned up, which I'm getting already. So I'm assuming that the VM is live. And let's start with this SSH again. Password. We are now inside the VM. We'll retry the docker ps command, and we see something. So this tells me how many Docker containers are running at the moment. So because we are seeing nothing in this list, means there's no container running at the moment. Okay. First command to know about Docker is docker ps. That tells us how many live containers are there. I also mentioned in my slide that there are live containers, there are suspended containers. So you can also do docker ps -a to see that whether there are any suspended containers, and there is one. I see there is one. And what happens in Docker, if you don't specify a particular name, it gives a random name. Okay, so there is a container running. I'm not sure which container is this, none of our concern, but there is a suspended container, which we can see by ps -a, but there is no live container, so there is nothing in the ps. Yep. Now, the next thing is the Docker images. So when you pull Docker images from a Docker registry, it goes into a local registry that you can access by typing the command docker images. And it shows some images here. These are some images I was testing last night. So it's there. If you want to get rid of images, so you want to kind of remove the images, these images would be the images which are already pulled in from the registry. I can do docker rmi remove image, and then I specify which image I want to remove. And this command takes multiple arguments. So I can say these three names. Okay. So the names are SPF client v001, SPF server v001, and the Python 3.12 slim. I can remove this by saying Python 3.12 slim and SPF client and SPF servers, and press enter. This will delete all my images. And if I now rerun the command docker images, I should be seeing nothing. So we are starting from a clean slate. We have no images, we have no containers running. All the codes are in the GitHub. We are now going to download or pull the GitHub repo and build the image on the fly. Okay. I also actually have this repo pulled in, so I'm going to remove that as well. rm-rf cloud native demo, enter. That makes this VM a clean slate. So I have no directory, I have no running containers, I have no images in my Docker registry. So let's start from pulling the image. So by now you should already know how to pull images from GitHub. I will go to my repository and I will go to my wait a second, cloud native demo repo that I already shared with you. You can also actually do this with me now if you wish. Go to the code, copy the HTTPS link, and this is the URL to the repo. And you must also have Git installed, otherwise you can't pull it. But now all the Linux distribution comes with Git pre-installed. So check first if you have Git or not, Git ---- version. And I already have Git. If you don't have Git, install Git with apt. So sudo apt-y install Git. Now, if we have Git, we can clone the repo by saying git clone space the link, the URL to the Git repo. We press enter, and because it's a public link, so you don't need any password or anything to download it. Once you clone it, you should be able to see the application resides as a local directory to the server, namely cloud native demo. We get inside this directory, cloud native demo, and we see the exact directory structure. Oops, tree is not installed, so let me just install quickly. That we saw for the application. So my present working directory is I am inside the cloud native demo. If I do a tree dot, means I'm going to see the directory structure of my cloud native demo. You see I have an app folder. Inside that I have a client, I have a server. The client is a Docker file, a main.py file, readme requirements, static and template, run.sh, same for the server. And then we have some other files, build.sh, push.sh, run.sh, and unrun.sh. Now, this way of structuring a software is dependent on the developer. This is my way of doing it, but mostly people do it in this way, but the name could be different. The build.sh file is responsible for taking the Docker file as input and build that image out of it. Clear? If I make any change in my code and I want to push that to first in Docker Hub as an image and GitHub as a code, I would run my push.sh file. If I want to run my application using Docker, I would use run.sh file. If I want to uninstall the application, I would use unrun.sh. Now, although it might sound complicated, but when you see the content of the files, they're extremely easy to read and comprehend. Starting with that build file. So if I say nano build, just 2 lines of code. I'm saying Docker build the image from the file in the app client Docker file. Tag this image, you give a name to the image, is SPF client version 001. And then you kind of get this file from what we call a context. That means in which directory this Docker file is. So it is typically this part of the file path, which is app client, and similarly for the server. So as a result of this command, what will happen? We're going to create 2 images. Okay. Let me show you how to do it. And let me show you one more thing. If I start with this, we're almost done with the demo. So I showed you already that if I say Docker images, I see nothing. Okay. Now I do chmod +x build.sh. So I make this file executable and I run build.sh, enter. I mentioned when I talked about cloud native, one of the feature is automation. Okay. What you are seeing happening now is the layers that we described in building the Docker image. It is now going through step by step, adding layers after layers, creating the image for you. All these things are happening through the Docker engine using the Docker's build tool, fully automated. Okay, so you first add the Python layer, add the requirements, add the files, install the prerequisites, and that's it. Once done, you can now rerun this command Docker images, and you should now be able to see these 3 images are there. The Python 3 image as a base shared by the client and the server, and the client and the servers by themselves. So we are somewhere here. Okay, so because you have pulled from the repository, so okay, we didn't pull from the Docker Hub. That is reserved for the next class. What we have done that if you are a developer and you want to run it locally, so you could put that build script inside the repository of the source code, and you can kind of create the image from there. Okay, so the building part is done. Now we're going to run the image. So you're going to create a running container from the image. So for that, let me take you back to the CLI again. And I mentioned, apart from the build script, there are also a run script. Okay, let's see what's inside the run script. So if I open the run script, this is where you see a set of arguments. Okay, so I'm saying Docker engine to run something, and it runs with 3 flags: RM, D, and P. RM means if I stop the container, instead of putting it to a suspended state, it will directly kill it. So you don't have to first suspend. You don't have to first suspend, means stop, and then kill. Rather, when you stop, it automatically kills it. So that's the RM flag. D is it stands for daemon. So when you run the application, it will not gonna occupy your CLI. You're gonna run in the backend. Then the port exposure. So what I'm saying here is this application is expected to expose a port, which is 9000 for the server, 9001 for the client. And this port will be forwarded to a port from the physical machine. I would slightly differ from what I said before, because I didn't want to get into the complexity that time. You can actually mix and match. You can expose a port internally, and you can expose a different port externally, and you can bind them. This is called port forwarding. If you're not sure what port forwarding is, rule of thumb, whatever is your inside port is your outside port. Okay. Um, Next is when I run the container, I should give a name. So I give a name flag, server, SPF server, and SPF client, and then the actual name of the image. So this SPF server v001 and SPF client v001, they are coming from Docker images. So these are the names. Okay, they have to exactly match. And the image name is to be the last component of your run command. So nano run.sh would have these two commands. So I'm telling Docker to run these two containers. So I'm going to bring it up from the image state to the running container state. So currently I am not running anything. So if I say Docker PS, I should see nothing, and that's the case. So what happens when I run .sh? Okay, so I have to first make this run.sh executable. chmod +x run.sh. It is now executable, and now I'm running run.sh. Press enter. What you see as an output are what is called an SHA. I think secure hash algorithm, SHA. This is a hash algorithm that gives you an ID that doesn't conflict. This is the unique identifier of a container. Please understand the relationship between the Docker image and the container is like class and object. You can create multiple containers from a same image. So just using the image ID, which you would have seen in the Docker images, this ID, this could be one ID from which you can spin up multiple containers. So this ID cannot be reused. So therefore, for each container, we need an SHA hash that will identify each running container independently. Now, because we ran these containers as a daemon, so we don't see them occupying in our screen. But what if I want to see what's going on behind the scene? You can see this by Docker log command, Docker logs. And then you can put the name of the running containers. So what are my running containers now? Docker PS. I have got one container named SPF client because I put the name in my run.sh file, and the SPF server for the server. So I can say, I want to see what is going on inside my SPF client container, and I should see some output. If you see what's happening here, this is basically the output that I'm getting from the Python script. UVCon is running. It is hosting itself over HTTP port number 9001, and it is accepting requests from every single IP. The process has started without any error. And I can also verify the same for the server, that is a server running without any error. That's the case. So this confirms the state that I mentioned here. So client and servers running in 9001 and 9000 respectively. They are being hosted by UVCon web server. And now if a client comes with this port number and the IP address on which it is being hosted, I should be able to access the client and the server.
So my doubt was on port forwarding. You mentioned that we can internally and externally exchange port.
Yeah.
So
okay.
How we can decide when to do this? Like what did I say?
Yeah, I see okay. A very good question. I will come back to this question in 5 minutes. Okay. Let me first show you the application because that needs a bit of explanation.
Okay, sir.
So the application is running. Okay. They are running as containers, and I can verify them. I can also do something. If you are familiar with tail-f command in Linux, so tail-f prints logs occupying your CLI. So if something happens, you can see those events coming live in your prompt. I can do the same in Docker logs. So I can say in the client that instead of just saying Docker logs, I can say Docker logs -f. And now you see what happened. My prompt is now reserved. It is waiting for new events to occur. And whenever a new event occurs, I will see them coming here. Why did I do that? Because the next thing I'm going to do, I'm going to run the client from my browser. So I'm going to run an HTTP client, which is the browser itself. I'm going to communicate with 9001. And as soon as I do this, my client will send a GET request, and I should receive a GET or POST request. I can't recall what request I put, but I should see some events here saying I've received a request from a client. So let's do it. 10.120 10.120.59.70:9001. And if everything is all right, I should be able to see the CLI, enter. So I can access the application, which is running as a container in the remote server, hosted in the port number 9001. And if that's the case, I should also see a log that someone has accessed the application, and this is the log. So from 10.120, 530, 253, 123 is my laptop's IP address. A random port number 6336 has sent a request, a GET request to the application, and the static folder inside that, the style.sh, style.css file has rendered, and the GUI has returned back as a response. That response you can see in your screen as this GUI. So I can do the same for the server as well. I can stop this log and I can redo this for the server. And again, the server is waiting for the event to happen. It is being hosted in 9000. Now, if we develop an application with Fast API, it gives you a default documentation tool called Swagger, and that you can access with the docs endpoint. So this is an example of a GUI that you haven't built. It is served from the Fast API micro framework, and you can see that the server has an endpoint called shortest path, and you can put documentation here that if you want to use it without a client, how should you use it? And this is an interactive terminal. I don't have time to discuss this, but if you wish, go and have a look in YouTube, what is Swagger UI and how to use it. Amazing tool coming by default with Fast API. What I'm going to do now, I'll go to the client and I'm going to say, hey, can you create a random topology of, let's say, 8 nodes? Give a prefix, let's say, router. So the node's name will be node 1, so router 1, router 2, router 8. So this client is saying that create a random topology of 8 nodes with a prefix router and run, let's say, Bellman-Ford, for example, to find shortest path. And my server is situated at 10.120.59.70, and the server port number is 9000. Just in case if you want to correlate with this server at 9000, client running in 9001. So when I do that, basically what I'm saying is the server to get a request from the client, this will be a post request. So I'm going to change the color. It will be a post request, and the server will do the path calculation, and you get the response back from the server. This is what is going to happen now. So I go to the client side again. I am waiting for the server to respond. So let me just put this side by side. So the server has not seen any response yet, except the docs that I just accessed with GET. And I press generate. something has happened. Okay, I have seen a random topology got created. And if I go down, I see a random graph was created. So this is the adjacency list representation of the graph. If I even go down, I see all the responses. So source router 1, destination router 4 is a direct path. Source router 1, destination router 6, there is no direct path. So the path goes through router 7. This is something calculated using Bellman-Ford. This is something the server does. So if I go to my CLI, I can now see that a post request was called. It was called on the shortest path endpoint, and the response was okay. That's my time. So we have seen in this tutorial that taking an application, a Python application, raw scripts, what are the steps to architect that application, encapsulating it into a container using Docker, how to build an image out of it. You can now see all these things I showed are listed in a tutorial section, so you can practice. And this script, unrun, build, and run. So you're going to stop the container, remove the images, and that's it. So one command to start from scratch, build and run the application, hence a zero-touch provisioning.
So that forward question.
Yes. So imagine you are a developer, okay? When developing an application, would you have any clue that how many ports will be in your server, which ports will be assigned to which applications?
So not an rough idea maybe, but not exclusively that I know that how many ports have reached.
Basically, you shouldn't have this idea. The reason is the target environment is different, right? That's up to the operation team. When you write the script, you have no clue how the script will be served. So therefore, what's the default port on any web server or web applications are hosted? 80 is a reserved port for HTTP, 443 for HTTPS. So if your application is only HTTP, then that's your default port. So when building the application, you only expose to port number 80. That's it. You don't care what the actual port through which this app will be served. So what happens when the op team will take your script, your Docker file will only expose port number 80, or sometimes use 8080 because 80 is a reserved port. And your Python application will take 8080 as well. So both your client and the server will have port number 8080 exposed. So when these containers will be live in the operational environment, so now I can say, all right, so the client will go to 9001. So I'm going to port forward 8080 to 9001 for the client application. And I'm going to port forward 8080 to 9000 for the server application. So that port forwarding, so your application will be exposed to a port agnostic to what actual port you're going to map with. The actual mapping will take place when the application will be onboarded. So this is something the op team will do. Clear? So when you, as a developer, write the application, you don't care which port to expose. You just put 8080. The operation team will take that port because all applications are in 8080, so they can play with which port they want to forward that application to.
Sir, I guess this is I was building this project with Kafka and using Docker Compose in its official image from the Kafka. And in environment, there are two ports, different ports, one internally and one externally. So I was a bit confused about this, that how we can decide that which port we have to connect to this so that it can work.
So the internal port must match to the port that you have exposed in your Docker file. The port that you define in the Docker file should match the port through which you run your application. So in my case, if you remember, in the run.sh file, I take the port numbers as argument, right? So that port number should match with my Docker file. Okay?
Okay.
Now, to which port you're gonna forward this, that's up to the deployment side. So for example, you wrote the application and you expose port number 8080, but for some reason port 8080 is already being used by some other application. So you are flexible now. You can forward that port to, let's say, 9090. Yeah.
Yeah, yes.
Okay. Any more questions? So yeah, that's my time, and okay, that's it.